Welcome to this session on hybrid electric discharge machining processes under the course Advanced Manufacturing Processes. In the previous session, we have discussed about the wear EDM process, its advantages, limitations, the principles of operations and other details including applications. In this session, we will study about the variant and hybrid processes in the EDM category, their unique advantages, process parameters, applications, advantages and limitations will be discussed. In fact, the capability of the EDM process, although initially conceptualized for machining electrically conducting materials, could be even extended to machining semiconducting and poor electrically conducting materials with continued research. As we know, EDM process is basically meant for electrically conducting materials, where the workpiece itself will be considered as one of the electrodes. Generally, it will be connected to the positive terminal of the power supply system and the tool will be connected to the other electrode or the other terminal of the power supply. Hence, the workpiece is considered to be one of the conducting materials or one of the electrodes. However, the main difficulty with this process is if the work material is non-conducting or semi-conducting, then the process efficiency either goes very below or it cannot be worked out. Therefore, different theories or different researches have been conducted how to enhance this capability with the help of some other technique. In a quest for enhancing its acceptability, the process is being hybridized with other phenomena of material removal. The total material removal rate in a hybrid machining process, which is the combination of two or more removal processes, say for example, two processes A and B, can be expressed as QV as in this equation. This is QV equal to Q of AB plus Q of BA, where QAB is the material removal rate of process A with the assistance of B and QBA is the material removal rate of process B with the assistance of A. Usually, Q of AB is greater than Q of A, that means material removal rate of process A with the assistance of B is higher than the material removal of only A. Similarly, the material removal of the process B with the assistance of A is higher than the material removal of B independently. Then the total removal rate of hybrid method is usually higher than the sum removal rate of either A or B independently. The same can be explained for other properties as well, particularly say for example, this can be applicable to surface finish as well. Say surface finish of A and surface, sorry, this is let us write in terms of surface finish, not in terms of surface roughness. So, surface finish obtained alone by the mechanism A and this is SFB represents surface finish by obtainable by, this is obtainable by mechanism A. then this is surface finish obtainable by mechanism B. Then if we apply in case of hybridization, surface finish obtainable by A with the assistance of B should be greater than surface finish that can be obtainable by only A. Similarly, the same is true for surface finish that is obtainable by B with the assistance of mechanism A should be greater than the surface finish that is obtainable by mechanism B alone. In these cases only, if this is true, then the hybridization is said to be fruitful. This is in line with the effect of hybridization as far as the material removal is concerned and as far as the surface finish obtainable is concerned. So, this hybrid EDM also aims to attain either of these objectives fulfilled, like higher MRR or enhanced MRR or the enhanced surface quality in the form of low surface roughness and high MRR through hybridization of two or more than two mechanisms. In many hybrid machining processes, besides contributions from component processes, some other additional influences also arrive. This is another significant point. This is not only that individual mechanisms A and B, they are complementing each other to get an enhanced output in terms of maybe material removal or in terms of surface finish, but it could help indirectly in achieving some other parameters getting right because of the hybridization or the combination of the mechanisms or combinations of the phenomena. These additional contributions may come from the interaction of the component processes. Combinations of different machining methods based on different kinds of interaction are being continuously attempted for enhancing the manufacturing capabilities in electric discharge machining process as well. Let us see some of the major cross or hybrid machining processes that are still under development at present. Some of these include abrasive electrical discharge machining, that is also called sinking or powder EDM, then ultrasonic assisted EDM, in short it is called UAEDM, then magnetic force assisted EDM, in short it is known as MFA-EDM, then electrochemical discharge machining, this we will discuss in details, then abrasive electrical discharge grinding, AEDG, etc. Let us discuss little details about the powder EDM. This is also a hybrid method in which free abrasive particles are added to the basic EDM process, which gives us powder EDM. As we have shown in the screen, both the mechanisms where abrasive action will also take place and the EDM action will also take place, and that gives an enhanced result of the process. So, it is a variant process of EDM. As we know, in EDM the material removal mostly takes place in the form of erosion of the materials due to the cavitation effect as well as thermal melting and evaporation of the material, work material, due to the high frequency sparking. The concept of this powder EDM was first introduced by Takahashi and his group of researchers in the year 1983. Thus, it is relatively a new process. In this process, when free abrasive grains such as silicon carbide powders are added to the dielectric, it reduces the electrical capacitance across the discharge gap by increasing the gap size. This results in higher spark dispersions and improvement in discharge characteristics. Commonly used powders in this process are graphite, silicon and aluminum. Application of powder mixed working media allows abrasive assisted electric discharge machining (EDM) to obtain mirror finishing in complex shapes with more uniform and crackless affected layers. The EDM process produces dyes without the need for removing the affected layer and can be effectively used for finishing applications such as in plastic molding and die casting. As we have already mentioned, EDM process is capable of producing very good surface finish. Therefore, it is particularly suitable for die making processes, etc. Adding powder of materials such as silicon in the dielectric improves the material removal rate and surface finish considerably. Addition of the ingredients such as solid powder and liquid improves the surface quality and decreases the tool wear rates. As we have already discussed, in case of normal EDM, along with the workpiece, the tool also gets eroded. Like if this is the tool and this is the workpiece, as we have seen in another session. So, this is workpiece and this is the tool. So, sparking takes place here. Now, because of this sparking, not only the work material will get eroded from this portion. So, this will go as debris in this process, but this spark at the same time will cause some erosion on this tool face as well. So, this will also go as small debris into the flowing dielectric. So, this is the dielectric flowing here, dielectric. Therefore, because of this small removal of material from this tool surface, the tool also gets worn out with continuation of this sparking process. However, if we use some powder particles here, then what happens? Principally, it works like this. This is the workpiece, this is the tool. Now, if small particles are there, abrasives are there, these are suspended on this dielectric. This is the dielectric flowing through this, which is an essential component in EDM. So, this is dielectric and these are the abrasives. So, what we call as powder and is the component, additional component in case of powder EDM. This is called powder EDM, whereas this is the conventional EDM case. Now, here because of this presence of these particles, the spark intensity will be smaller, or we can say in other words we can say this sparks will be more distributed. So, these are say sparks and these are sparks. Now, in comparison to the previous cases where more concentrated sparks were produced, but here in the powder EDM cases the sparks are more distributed, we can say more distributed, and therefore, the erosion, corresponding erosion that is taking place will be in the smaller quantity. So, this is the debris produced because of this powder EDM, which is as far as the quantity is concerned, which is less in comparison to the previous cases. So, this ultimate effect or this results in the reduced tool wear. Because of this, the near to mirror finish can be obtained by using the correct combination of aluminum and other powders. This also gives relatively higher machining rates through the use of negative polarity for the electrodes. Silicon carbide powder has also been tried with pure water, and it results in increased fluid electric conductivity, increase in the material removal rate, and it also helps in extruding the debris away quickly. This is another important factor, as we have discussed while discussing the basic EDM process. The debris that gets produced during sparks or the erosion should be taken away from the machining zone as early as possible. Otherwise, this accumulation of this debris can clog the gap in between the tool and the workpiece. That is what is we call popularly as inter-electrode gap. And if this gap gets clogged, there will be a short circuiting conditions, and no longer sparking will take place, rather the circuit will be completed and the current flow takes place. Therefore, the basic phenomena which is responsible for producing the material removal or the erosion of the material removal will not take place any further. Therefore, in EDM related processes, it is very important to take away the debris as early as possible, as quickly as possible from the machining zone. And in powder EDM, with the help of suspended particles, powder particles, this may be silicon carbide as we have seen just now, it can be aluminum powders or it can be graphite powders. This is possible in a more efficient way. The electrorheological fluid consists of dielectric particles suspended in the insulating fluid. In such an application, the combined process of EDM and polishing have been used to get better surface finish, in which average roughness is obtainable to the tune of 0.08 to 0.06 micrometer using alumina abrasives of 0.3 micrometer size, and polishing of the recast layer could be obtained. Using titanium powder, green compact electrodes, a new process for coating on the workpiece, which is known as electric discharge coating, has also been reported. This is another variant of this electric discharge machining process itself. The basic mechanism is EDM, and then the coating, which is addition to this EDM process, is being done in the same process. This process is capable of producing a ceramic layer on the workpiece, thereby increasing its surface hardness, and can be taken as a coating process. As we know, ceramics are known for their enhanced hardness or higher hardness. So, therefore, in this process, simultaneously, if we can coat a material like this, say alumina or silicon carbide, which has got much higher hardness, onto the machined surface, then the machined surface will acquire better hardness as a result of this combined process. Therefore, it can be termed as the hybrid process, in which we are getting better results than it could have been with a single phenomena. Cloquet and his co-researchers have carried out substantial studies on the effects of recast layer by using microjoule range discharge energies in combination with powder suspended working fluids. The analysis shows that aluminum powder leads to thinnest rim zones at higher material removal rate. It is also reported that the silicon powder produces a gray zone beneath the actual white zone. Wu and his co-researchers have used aluminum suspended 0.1 gram per liter along with the surfactant 0.25 gram per liter to get up to 60% improvement in surface finish compared to normal EDM. So, this result suggests that the hybrid process is giving us substantially better result, in which 60% improvement in the surface finish can be obtained. So, this process can be useful where high surface finish is required, as well as where intricate shapes are to be machined, which is usually very difficult in using the normal process or conventional machining processes. But if we go alone with the electric discharge machining process, the surface finish results are not very good, as we have already discussed in several other sessions. But the same surface finish with the addition of some other technique, we can enhance to say 60% or 70%, which is quite substantial or beneficial as far as the productivity or the cost of machining or production is concerned. In this process, the surfactant molecules act as static barrier to separate the agglomerated aluminum powder and disperse them within dielectric, thus improving the surface finish. Now, let us move on to another process that is called ultrasonic assisted EDM, also called UAEDM. This is another hybrid process of EDM. In this process, as we can see in the figure later, it is recognized that the role of acoustic wave and cavitation phenomena improve the flushing and material removal from the surface craters. These process conditions are significant for micro drilling and production of slots and grooves. In such a case, the vibrations can be given either to the tool or to the workpiece with a suitable attachment. As we have already discussed while discussing ultrasonic machining, in ultrasonic machining, ultrasonic vibrations can be given either to the tool or to the workpiece. but in most of the convenient ultrasonic machining processes, giving ultrasonic vibration to the tool is considered to be more convenient, while in case of micro ultrasonic machining, giving ultrasonic vibration to the workpiece has been considered as more convenient process. Similarly, in this process, ultrasonic assisted EDM process, either tool or the workpiece can be given this ultrasonic assistance, which will help in removing the debris more efficiently. Here is the principle explained. The figure is on the screen. This is the tool which is responsible for the ultrasonic vibration. So, as usual, as in the case of a normal ultrasonic machining, this tool head will be connected to the horn as well as the ultrasonic generating equipment, and this is the abrasive slurry which will be introduced into the gap between the tool as well as the workpiece. Now, in this particular configuration, we are trying to show that the ultrasonic vibration is given to the tool itself and the workpiece will remain stationary. Now, here both the actions will take place. The normal EDM, because of the dielectric being flown here, which is nothing but the form of the slurry, in which some abrasive particles are also suspended. These abrasive particles in turn will take part in this ultrasonic mechanism, which we have already discussed in several sessions. Therefore, here both the actions will take place. Ultrasonic machining, because of the tool, vibrating tool hitting the abrasives which are suspended on this slurry, and then the discharge that is taking place in this tool and the workpiece gap, tool electrode, inter-electrode gap. Therefore, the combination of these two processes will give enhanced machining performance. It can be either, as we have already discussed, in the form of material removal or in the form of enhanced surface finish. The vibrating movement of the tool electrode or the workpiece improves the slurry circulation and the pumping action by the pushing debris away and sucking new fresh dielectric. It provides ideal condition for discharges and gives higher removal rate. Kramer in the year 1986 reported the earliest application of ultrasonic machining with electric discharge machining using graphite electrodes. Another beneficial effect that has been observed is concerned with the structural modifications because of this hybridization. The high frequency motion of the electrode and the workpiece due to ultrasonic wave creates more turbulence and cavitations, and this results in better ejection of the molten metal from the craters. As we have earlier discussed, the molten materials, because of the discharge action or melting and evaporation action, if they are not removed from the gap quickly, then there is a possibility that this molten or semi molten material will get adhered either to the tool or to the workpiece, that forms ultimately a white layer or additional sputtered layer on the tool or the workpiece. This can reduce the further sparking rate, resulting in reduced performance of the process. But here, because of the continued ultrasonic machining process or the ultrasonic vibrations, there will be cavitations continuously taking place, and that will cause the ejection of the molten material from the zone, machining zone, and will be subsequently flown away by the flowing dielectric fluid. Therefore, the consequent formation of sputtered layer or the white layer phenomena will be reduced. This increases the removal rate and less material recasts on the surface. Thus, structural modifications are minimized, less microcracks are observed, and the fatigue life is increased. Associating EDM and USM can lead to considerable improvements in the production of complex shape workpieces. Yan and his co-researchers used circular tungsten carbide rod of 0.3 millimeter diameter and suspended silicon carbide grains as abrasive particles in kerosene media, which works as dielectric, in another attempt for hybridization of this process. The setup is a combination of micro EDM with ultrasonic vibrations, in which fine micro holes could be drilled on hard and brittle borosilicate glass. Prihandana used suspended micro molybdenum sulfide powder in the dielectric fluid and provided ultrasonic vibrations onto it. So, these are different attempts by different researchers to make the ultrasonic machining and the electrical discharge machining processes work together in order to enhance their performance. Significant improvements in surface finish and metal removal rate, along with flat surfaces, free from black spots were obtained due to this combined effect of powder EDM as well as ultrasonic machining. In this study, tools were made of brass and machining was carried out on copper, copper tungsten and silver tungsten material. A new hybrid method using planetary movement with enhancement from ultrasonic vibrations on an electrode was developed by Yu and his co-researchers for micro hole drilling. It was found that the use of these hybrid methods can give unevenly distributed gap for bubbles and gases to escape. Cern and Swang designed a vibrating work table and employed it in mass producing of micro holes using EDM. This also can be considered as a kind of modifications in EDM in order to have better effect of the process. Using titanium powder in dielectric on aluminum, zinc, magnesium alloy, it was found that the machining performance increases significantly. This was first reported by Chen and Lin. However, an alloyed layer with improved hardness and wear resistance was found on the machined surface. The results show that the efficiency increased considerably. Holes with diameters of 200 micrometer on SUS 304 stainless steel and brass were successfully drilled with this method. Now, let us move on to another hybrid process, that is magnetic force assisted EDM. In this process, magnetic field has also been used effectively with the normal EDM machining process. The typical setup consists of magnetic field consisting of a rotating disc, motor and magnets. The magnetic field is created in between the electrode and the workpiece. This helps in driving the removed material away from the zone, thereby increasing the efficiency of the process. In a study on magnetic force assisted EDM, Lin and Lee have reported that for improving the machining performance, expelling the debris from the gap quickly was critical. As we have already discussed, debris removal from the inter-electrode gap is very critical as far as the enhancement of the performance of the EDM, normal EDM process is concerned. Hence, an additional motor was used by these scientists with 2 magnets, which enhanced the performance of the system. The magnetic force assisted EDM facilitated in improving the material removal rate up to 3 times the conventional EDM, which is quite substantial. The surface cracks were relatively less, but the electrode wear rate was slightly higher than what is observed with electrochemical machining. The experimentation was tried on SKD 61 stills using kerosene as the dielectric fluid. Low and Chen first reported the behavior of pulsed EMF, which influences the surface roughness, especially in superfinishing EDM. The use of magnetic force in EDM is primarily to remove the debris from the discharge zone. By applying short discharge pulses, very smooth surfaces up to 0.04 micrometer of average roughness could be achieved. In another experimental study using Taguchi methods, Lin and his co-researchers have found that the relative electrode wear rate improves by around 0.33 to 1.03% along with the increase in material removal rate. Now, let us move on to some new developments in wear EDM process. In a variation of the WEDM process, Menzies and Cauchy combined wear EDM and wear sawing. It is a hybrid process involving phenomena of material abrasion and spark erosion. In this process, a new embedded wear was used bonded with alumina and diamond, and the improvements in material removal were reported using new solid state generators. Some studies also suggest that in WEDM, low conductivity of the dielectric should be incorporated for discharge sparks to take place. It was found that an AC pulse generator and low conducting dielectric provide better surfaces with reduced surface cracks and residual stresses. By Wegener and his co-researchers have designed and developed a special wear electric discharge dressing WEDD unit and integrated it with a grinding machine. In this system, which is also a hybrid system, high material removal rate, higher accuracy was achieved using metal bonded diamond grinding wheels. Now, let us move on to another process that is called microelectric discharge machining process. In micro EDM, the principle is almost same with that of the normal electric discharge machining process. This process has also a servo system with high sensitivity and positional accuracy, which is something near plus minus 0.5 micrometer. This permits the setting of minimized discharge gap of 1 micron. Thus, the system is suitable for conventional precision engineering purposes as well as for micro component fabrication like micro molds and micro inserts. Micro EDM is very challenging due to the difficulties arising in reduction of scale of the process. Fabrication of small electrodes having small inter-electrode gap, achieving accuracy, removal of debris, keeping HAZ or heat affected zone to a minimum are very challenging issues in micro EDM. In order to make the micro tools, the wear electric discharge grinding WEDG method is used. The WEDG method can be performed on the same wear EDM machine. In order to improve upon the electrical geometrical characteristics and roughness of microelectric discharge machined features, electrochemical polishing is preferred on it. Specific tooling applications of this process. EDM is commonly used for making tool and dies. Typical examples being number 1, hardened steel dies, stamping tools, wear drawing and extrusion dies, header dies, forging dies, etc. Let us see another variation in this EDM process in which machining with electric discharges in deionized water was attempted. In this process, Karodew and his research group have used a new EDM process with polymer carbon electrode material which could be molded repeatedly into complex geometries and used to perform precision EDM machining in deionized water. This is a novel process used to perform automated finishing and polishing operations of electrically conductive material parts, which reduces development time and cost of tool steels that are used for mass production of broad variety of commercial products. Another variation is ECDM. This ECDM is another hybrid process. This was initiated by Kara Fuji. The process is mainly used for machining non-conductors such as glass, ceramics, quartz, granite and composites, etc. This process we will discuss in little more detail later on in another session. Then let us look at the possibilities of electric discharge machining of metal matrix composites, which are also commonly known as MMCs. The EDM process requires electrical conductivity for spark initiation. Hence, trying with MMCs having metal ingredients with some other non-conducting materials such as ceramics or composites was a possibility. A summary of machining of MMCs by EDM is shown in the following table, which we will see shortly. Lawyers et al. First reported the existence of oxidation and dissolution as other phenomena apart from melting, evaporation and spalling in EDM. These had opened up the possibilities of applying EDM successfully for machining of materials like MMCs. Electrically conductive materials like TIN, titanium nitride and TICN were added in the trials on zirconium, silicon and aluminum based ceramics. These are some of the attempts on machining of MMCs using EDM. Mohan and his co-researchers have suggested one process. This is rotary tube EDM process. Then George and his co-researchers, they have also used EDM process for carbon-carbon composite machining, and they have reported increase in the MRR. Then alumina and aluminum silicon composites were machined in another attempt, where people have observed the surface degradations and inferior surface integrity have been found. Then EDM and laser processes were studied and reported that EDM gives better or thermal damages, less thermal damages than the laser beam machining. This was done on silicon carbide with aluminum alloy, that is also another kind of MMC. By infiltrating free silicon into the silicon carbide, the electrical conductivity of the matrix largely improved, and therefore, the machining performance became better, and this made the material easily machinable by die sinking EDM. Now, let us summarize what we have discussed in this session. The concept of EDM is quite old, that we have already seen, yet it is being commonly continuously innovated through new hybrid technologies. Future generation industrial requirement is to process materials and composites with highest material removal rate, least material wastages, that means the lean manufacturing approaches, and to cater to the continuously increasing demands for higher accuracy and higher quality. Miniaturization has resulted in new challenges to develop hybrid and variant processes which can achieve these requirements efficiently. Micro EDM is the most potential area which needs to be further developed. It needs to be integrated with technologies such as magnetic assisted EDM, abrasive assisted EDM, and ultrasonically assisted EDM for conducting materials. ECDM and powder EDM for machining of non-conducting materials, ceramics and composites are better options. We hope this session was informative and useful. Thank you.